Okay, this is the pre-lab video for the experiment in which you'll build your own diffraction spectrometer for Physics 2213. So in this experiment, you won't be using the laser. The laser will be probably still mounted on the table, but it'll be out of the way and you won't be using it. You will be using a number of different LEDs as your light source, which will be attached on this little piece of foam. And these LEDs all look the same. They all look clear, but there's three different colors here. One is green, one is red, and one is white. And so you'll be investigating those. So your first goal is to, or the first step is to use either the red or the green one. I guess they have little marks associated with them. The green one has a little green dot on the side, and the red one has a little red dot on the side. So find the green one to start, I suppose, and it has to get mounted in the LED power supply, which is here. This is just a little device which uses the 5 volts from the USB port on your computer to drive the LED. And so here's the important part. As you know, diodes have an anode and a cathode, and the anode and the cathode typically on actual diode devices are designated by one having a longer leg and one having a shorter leg. One of them is positive, one of them is negative. So the anode is the positive, and the anode is the longer leg. And so to power this, we take the longer leg and we put it in. There's two little holes in the face of this LED driver, and we put it in, and the LED lights up. Now, it's tricky to put this in. The LED slides in really nicely, or relatively nicely, but if it's not going in perfectly straight, it's kind of tricky. So you wouldn't force it, because you'll end up just bending the legs on the LED or damaging the mount. You just try and jiggle it around until you find a way in which it goes in smoothly, and the legs don't feel like they're getting caught too much. Okay, so this LED is not quite a laser, and it's not quite an incandescent light source. It's not broadband, but it's not as narrow as a laser. Lasers are typically very narrow wavelength band. LEDs, as you're going to see in this experiment particularly, are reasonably broad, 10 or 20 or 50 nanometers broad in terms of their frequency spectrum. And so this green, although it looks green, there is a range of different greeny, yellowy colors comprised in that green. The other way in which an LED is different than a laser is it's not very directional. So this light you're actually seeing on the camera right now, because some of the light is coming off to the side. So this light is getting distributed over this bigger solid angle, whereas a laser is very directional. Right? A laser, you just have a very thin beam. Here it's a very spread out beam. What we would like is a more thin looking beam. And so what you're going to need to do is to put a lens in front of this to collimate it. Now, putting a lens directly in front of the LED isn't going to do very good, because the LED is not very much like a point source. And so, you know, what you would want to do, what you think you might want to do first, is put a lens in at one focal length away from the LED, and then what you'll have is a collimated beam. But that doesn't work all that well. So what you want to do is make this look like a point source. And to make it look more like a point source, we're going to put it through an iris, which is very much a very small iris. So that iris gets put in place, and what passes through the iris is now a very small point of light. Now, if one were to put a lens in front of this point of light, then one can get a collimated beam, because this is actually looking like a point source of light now. So it's sort of a cleaning up our light source in some sense. What we really don't want a collimated source of light, because then we'll have a big beam coming out here. What we want is a focus light source. So the lab manual takes you through the optical setup. You want to stick a mirror somewhere between your collimator and the diffraction grating, such that the light from the LED is focused somewhere after the diffraction grating. So the diffraction grating will already be mounted for you. It's mounted at some angle. It's mounted at an angle, and it's going to diffract, it's going to reflect the light off to the side, and some of that light is going to be diffracted as well. So you'll not just see one green spot over here, you'll see a number of green spots corresponding to the different orders of the diffraction. The angle by which the light is diffracted off of the diffraction grating, right, you'll have your 0th order reflection, and then you'll have these different dots corresponding to the diffraction. The angle of the diffraction depends on a couple of things. It depends on the parameters, the physical parameters of the grating itself, but it also depends on the wavelength of light. So the angle that the light comes off depends on the wavelength of the light, or the color of the light. So if we use a green diode, it's going to come off, the first order diffraction beam is going to come off at a particular angle. And if we use a red LED, a red light source, the first order diffracted beam will come off at a different angle. And so that way, well, that's how diffraction gratings work. So what we then want to do is put a CCD camera somewhere to look at the first order diffraction beam. So our CCD camera will get mounted somewhere to look at the first order diffraction beam. And the idea is we want to be able to look at the whole visible spectrum. And so if we have this too far back, such that the first order diffracted green goes into the CCD, but the red misses the CCD, then we haven't really accomplished anything. That's not the device we want to make. We want our sensor, our active area on this camera, to be able to view everything from blue all the way down to red. Right, the entire visible spectrum, purple down to red, maybe you would say. And so there's a optimal distance that this should be. If the CCD is too close, then the green and the red and the blue aren't going to be very much separated. If this is too far away, then they'll fan out too far. The green, red, and the blue will fan out too far, and we'll miss them all. So there'll be some optimal distance that this has to go. Once you figure out where this has to go, you just want to adjust your lens such that the light is focused at this location, at this plane. Okay, so the optical setup is going to take you some time. It's going to take some thought on your behalf to figure out how this all works and why it all works the way it does. But once you do that, then you want to start looking at the signal you see on the camera on the computer. And so let's just have a very quick look at the computer. Most of the details are in the lab manual. But I guess I'll just say that you run this software called AM Scope. And if the USB cable was connected to the camera, you won't see anything when you open it until you click on, from the camera list, you select the camera that we have attached. And this, in this little field there, I'm not sure if you can see this at all, but in this field under the camera list pane in the left tab, in the left window, you should see the camera, and when you click on it, you'll start to see an active image. And so that's how you get started, and the lab manual takes you through various exercises to get acquainted with this software and to take you through the exercises you need to do to understand how your spectrometer is working that you built. Okay, so again, operationally, the trickiest setup thing for you is probably going to be inserting these LEDs. Right, so they just pull out and push in, but there's a positive and a negative side to these LEDs, and you have to just fiddle around with them just a little bit so that they push in, and they should push in nicely and completely all the way so that the legs are all the way pushed in and you can't push it in any further. And so there you go. That should be enough to get you going. Good luck.